Well, good afternoon, everyone. Today we are starting a series of seminars with people who have been successful in one of the IRC calls, either starting or well, we are getting researchers that in all the levels where the IRC calls can be granted. And today it's my pleasure to introduce you to Raúl Angulo. Raúl Angulo, who is currently working at the IPARCOS Research Center in the country Vasco, but he started his scientific career in the UK, in Durham University, where he completed his PhD thesis in 2009. His thesis, furthermore, was considered like the best thesis in the area of physics by the Durham University. And after that, he went to the Max Planck Institute for Astrophysics to work in the group of Simon White. And then he got one of the famous Cavill fellowships to work at the Cavill Institute at the Stanford University. From the US, he came to Spain to work at the FEFCA Institute in Teruel, where he was one of the persons who helped to build the JPAS project. He was granted with the ERC starting fellowship in 2016, and currently he's, as I say, he's at the Bass Research Center. He's going to talk today about his work and about how to learn about cosmology and galaxy formation with numerical simulations. And also he will tell us a little bit about his experience with the RC code. So whenever you want, Raúl, thank you for being here.
Well, thanks a lot for the introduction and for the invitation. So we'll start sharing the screen. Okay. As I was saying, thanks a lot for inviting me. And so, you're seeing the presentation mode, right? Yes, I guess so. So I'm going to talk about how we can use numerical simulation, cosmological simulations, to understand more about our universe and fundamental physics. So I'm currently at the Donostia International Physics Center, hired by the Iker Basque Foundation in San Sebastian. So one of the main questions that cosmology and cosmological simulations try to answer is to explain the universe that's around us. And so when we make maps of the sky and of our universe, we see this, for instance, this distribution of galaxies. In this case, this is the Hubble Deep Field. And we see galaxies of all sizes, colors, with many different properties, and they are also arranged in peculiar patterns, right? We see this, the so-called cosmic web. So it's shown in the right. This is the Sloan survey, and you see that galaxies are not distributed randomly in the universe, but they have all these patterns, right? So one of the main questions that we want to answer in cosmology is why the universe it is like it is, right? And can we use the observable properties of the universe to learn about fundamental physics law, like what is the correct model for particle physics, or the correct gravity law, and maybe we can learn more about our place in the universe. So, over the last decades or so, cosmology have seen this transformation. I'm sure you're all aware, starting from a very qualitative science to a very high precision one nowadays. So a lot of this progress has been driven by cosmic microwave background experiments. And this is an example of the measurements by the Planck satellite. And here you can see this, the polarization and temperature and isotropy power spectra, right, in the y-axis as a function of angular scales. So the symbols is the data, the measurements. So we can now measure this radiation from the early universe to super high precision. And we have been able to use this data and learn about the universe, not only because of the exquisite quality of the data, but also because there is a equally accurate theory, which is these solid lines, right? So this is the best, the theoretical model that best describes the data. So you can see that the agreement is superb, right? From very large scales on the left to the very small scales. And from this data alone, we have learned already quite a lot. For instance, that we know that we need some sort of cold dark matter, something that's non-interacting or not strongly interacting, at least electromagnetically. We need this component at around 100 sigma. We also know that it cannot be that has to be relatively cold. We know that the initial fluctuation spectrum is not scale invariant, but there is some scale dependence, and that might hint of some issues of inflation. I'm going to mention this later. And from these measurements, we can also derive the, for instance, the optical depth and the amount of baryons, for instance, and so on. So this is really, really remarkable because has supported or what has emerged is this so-called standard cosmological paradigm, this lambda CDM model. And it relies on essentially 4 key ideas. One is that general relativity is the correct gravity law, and that's the dominant force on large scales. It also relies on the existence of dark matter, the existence of dark energy explaining the late time acceleration of the universe, and also relies on inflation as the physical mechanism to create the initial seeds for growth of the structure. And in this lambda CDM paradigm, we can explain not only the CMB fluctuations, but also many other, essentially all cosmological observables, from strong and weak gravitational lensing to the spatial distribution of galaxies, or from the absorption lines in the light from super high redshift quasars, right? So all these measurements of cosmology that probe very different aspects of the universe, they all seem to agree with this cosmological model. So on one hand, this is really, really remarkable, right? We have a relatively simple model that explains such a complex and diverse data. On the other hand, it kind of it's a bit of a bittersweet taste, because even though we can explain the observed universe, we don't understand the nature of any of these ingredients, or there could be rooms for additional physics. For instance, regarding the gravity law, maybe it's GR, or might be other more complex theories like this FOR or Galilean, and on these super large scales, we haven't really tested accurately what gravity is like. Likewise, the expansion of the universe is consistent so far with a cosmological constant, but there could also be a time-dependent equation of state, or could be some coupling between dark matter and dark energy, and there could, this dark sector could be very rich. About dark matter, we don't know exactly what temperature, or whether they might have some quantum properties on macroscopic scales, or there could be also interactions on cross sections with itself, could annihilate, or there could be a lot of additional properties that we have not discovered yet. The only contributor to dark matter that we know should exist are massive neutrinos, but we still haven't pinned down exactly what the contribution is. And finally, about inflation is the leading theory for explaining this early universe, although it still is not proved at all, and there could be a lot of mysteries associated to inflation. We don't know whether it was driven by a single field, or it could be many different fields. We don't know the energy scale in which it happened, and so on. So a lot of the cosmological research nowadays is about breaking lambda CDM, finding the places where lambda CDM does not work, right? And that could be, for instance, some examples are attempts to measure non-zero curvature, or measure the masses of neutrinos, or the effective degrees of relativistic degrees of freedom. But so far, all of these measurements have been consistent with the simplest lambda CDM model. So this is, on one hand, there is this kind of consistency, and there hasn't been anything significantly detected. But on the other hand, there are tensions, right? There are things that don't quite match, especially when we compare the high redshift universe that probed by the CMB with the low redshift universe. And then there are the two kind of most famous tensions, are the Hubble parameter one, where the CMB measurements are about 67, whereas various late time probes from time delays and or supernovae, they tend to prefer values are about 74 or so. This is like a 2-3 sigma tension. And another tension is that refers to the clumpiness of the universe. Again, like all the predictions or extrapolation from the early universe indicates, or within the lambda CDM, you expect a universe that's much clumpier than what you measure from the low redshift universe through redshift space distortions or gravitational lensing or even clusters. They all seem to prefer values here shown about 0.75 or so for this clumpiness factor S8, whereas the Planck and CMB measurements seem to prefer values of 0.83 or so. So there are these two tensions. So now we are in this place in cosmology where we have on one hand a very successful model, but we also have these tensions, and we don't know whether this is telling us that the universe is much more complicated than what we think, that we finally found where lambda CDM cracked, or it's simply that there are unaccounted errors either in the data or on our modeling. We're misinterpreting the measurement. So how do we proceed from now on? Right? On one hand, we can keep going and through improving the CMB measurement, what has been so far our main source of cosmological information. But unfortunately, that is, even though you still could get much additional information, a lot of these tensions come from the low versus high redshift universe. So the last structure of the universe offers a new window towards high precision cosmology. And there is a lot of potential from mapping the low redshift universe as a way to measure cosmology. And the reason why this is actually pretty simple, right? That the structure of the universe, the distribution of galaxies, gas, and dark matter, depends on these fundamental aspects of the universe. It depends on the components, the amount of dark energy, dark matter, radiation, depends on what the initial seeds were. So this might be sensitive to primordial non-Gaussianities, and in general, the shape and amplitude of the primordial fluctuations, and depends of everything in between, right? All the physics that drove those initial fluctuations to their present day state, from the gravity law to the galaxy formation physics, hydrodynamics, and so on. Right. So the current state of the universe is encoding all this rich physics. And in addition, because of it's a three-dimensional map of the universe, in principle, there is much more information than the CMB, which is only like a 2D image of the universe. And this is a huge opportunity for cosmology and for physics, I would say, and that's why there is a lot of interest on it, and there is a lot of observational endeavors that have jumped into this opportunity, from Euclid, LSST, and passed by JPass and eROSITA, various of CMB stage 4 experiments. And they are all measuring the large-scale structure of the universe to super high precision and in different ways, right? Some of them will focus on weak gravitational lensing, where they're going to map the distortion of high redshift galaxies induced by intervening matter, or the clustering of galaxies, or the abundance of clusters, or other effects such as the Sunyaev-Sedlovich effects, or intensity mapping, right? So we are going to have this kind of multi-probe, multi-frequency measurement of the universe and of the large-scale structure. So one of them, I would say, most pressing questions for theoretical cosmology nowadays is also, we are going to have all this huge amount of data. How do we actually come about exploiting it, right? Extracting all this information that there's going to be like petabytes of data, like super accurate measurements, and now we need to get the cosmology, get the physics out of it. So how do we do that? So traditional in physics, this is anything you can think of, you can put in this kind of dichotomy of an observation and experiment, and you have a theory, right? And you contrast your theory, your predictions with the experiment, and then you can rule out or confirm something, right? You could have a theory where you have the law of gravity is something very different to GR. We contrast it with an experiment, and then we rule it out, right? Or we can confirm eventually some unknown physics. But the problem is that for large-scale structure, there is not really a theory, right? And making prediction is a super hard problem. So I'm going to give you a flavor of why that is. So we have to start with the initial fluctuations and the ones that, for instance, the CMB observes, and these are relatively easy to predict, right? They're like Gaussian, they're described by linear perturbation theory, so we can actually write down the equations and have a super precise prediction for what the CMB should look like for almost any theory, right? Or at least from lambda CDM and reasonable departures from it. So we can exploit it effectively, right? As I was arguing in the beginning. But when we go to the low redshift, then things become more complicated because gravity makes all those small Gaussian fluctuations evolve into a nonlinear state, right? So all these fluctuations would collapse. They will have a highly non-Gaussian and nonlinear field. There is the formation of dark matter halos, this collapse structure which will host galaxies, and the formation of these halos is in itself non-local. There could be some stochastic fluctuations and involves complex physics. And it's not only gravity what we need to account for, but it's also baryonic physics. We measure in many experiments galaxies and that are themselves are bias objects. Again, there are nonlinearities and non-Gaussian features. And we infer the velocities from redshifts, and velocity itself could be also biased and nonlinear and so on. There's also the gas physics, and on top of that, all the observational issues, right? That selection functions, livelihoods, that you need to characterize accurately, right? So we have these complex problems that we will need to solve to be able to write down a theory for large construction. And that is current, and this is super important, right? Because the smaller the scale that we can probe, the better the description, we are going to end up with stronger constraints. And well, I think okay. So let me mention this first. So right. So what we can do is make some simplifying assumptions, right? So we can assume that only large scales are important, and in there we can apply certain symmetries and describe the dynamics of the system in a perturbative way. So we can actually end up with some sort of theory for large scale structure that works on certain scales, typically very large scales. But the price that has is that we only partially exploit the amount of information that there is in large scale structure. So this is an example. For instance, let's focus on the neutrino physics. And then the red line is what current models achieve, right, in terms of constraints on neutrino masses. So if we are able to go to scales that are twice as small, now we can extract about 3 times more constraining power on neutrino physics. So this factor of 2 is what we hope to achieve in the next couple of years with much more sophisticated perturbation theories. But if we had model scales down to 0.5 h over megaparsecs, then the amount of cosmological power would be about 30% larger. Right. So the reason for this is that when we observe the universe, the units of information that are on small scales scale as the third power of the scale. Right. So you have a volume that if you measure only very large scales, you only have a few of those of pairs. Whereas if we focus on small scales, we have cube times more data. So therefore, we can put much stronger constraints. So right, so I was telling you that so going to small scales and nonlinear scales is important. We cannot do it with current tools, but on the other hand, we have another way of predicting what the nonlinear universe is, or what it looks like. And that is simulations, like this, what they call the third leg of science, right? Where you take some complex theory, and then you, even though you are not able to analytically propagate what that nonlinear physics is, you can simulate it, right? And well, we know in cosmology and in galaxy formation that is something is essentially the most accurate way that we have to predict the universe, right? So the basic idea is that we take this initial fluctuation, the Gaussian linear that we're able to predict, we write down the equations of physics, or the equation of motion and the laws of physics that we think is are relevant, and then we solve those equations in large supercomputers. And here are some examples of several simulations, like the Millennium or the Bolshoi, and nowadays it's becoming more and more common to also have these simulations where, including the full from hydrodynamic forces and galaxy formation physics and gas physics, and these are the Illustris or Horizon AGN simulations. Right, so this is kind of a well-known field in cosmology and astrophysics. So, but then it's particularly a super interesting one, because I think it involves a lot of different physics, right? So on the large scales, we need to solve for general relativity, how the universe expands, and also the gravitational dynamics. Then as we go to smaller scales, there is the nonlinear collapse of these initial fluctuations, and in this formation of halos, where gas eventually is going to accrete and cool, and galaxies merge on the centers of these halos. And in these galaxies, there is star formation and evolution. And in the centers of galaxies, we think there are these supermassive black holes, that once they accrete material, they can emit through jets energy back onto the large scale structure of the universe, and modify scales that naively you would think they're only affected by gravitational dynamics. So we have all these complex physics, right? That are all these different scales that are actually connected to each other. So that makes the problem challenging, but also super interesting. So the question I asked myself was, okay, so we have all this new data. We don't know how to optimally exploit those because all the traditional large scale structure theories work only on super large scales. And on the other hand, we have these super accurate simulations of the universe. So I asked myself, can we use these simulations as the large scale structure theory? Right? So what does it mean? So it means that for a given cosmological model that we want to try, a given gravity law or so on, we could run, or we can perform numerical experiments of the universe, right? We can do a cosmological simulation, and in these simulations, follow the galaxies and gas and so on, and make predictions for the three-dimensional universe that then we can analyze in the same way as the data to then compare a given summary statistics, for instance, the correlation function, abundance of galaxies, and so on. So and you do this inside for instance, a livelihood sampler. So we will try hundreds, thousands, millions of combinations of different cosmological and galaxy formation parameters to then compare against the real universe, even down to small scales, and derive constraints on physics, and perhaps even make some discoveries. So so that was actually the goal of my ERC, or this is what I propose for my ERC, to try to do that. And yeah, so this is what I've been working on with a group of people in San Sebastian, and I'm going to mention some of the results we have obtained, in particular from Marcos Pellejero, postdocs, and Sergio Contreras, Jens Stucker, and Mateo Senaro, and three PhD students, Giovanni Ericó, Lourdes Ondaro, and Daniel Lopez Cano. Okay, so to have numerical simulations as the large-scale structure theory, we need to solve many different challenges and problems. Right? I'm going to group them into roughly three areas. The first one is to be able to predict the nonlinear dark matter distribution for a given cosmological model, and for that we need efficient, robust, and accurate simulations. We need to sample a high-dimensional parameter space, right? So we need to be able to vary the amount of curvature, amount of baryons, or the amount of neutrinos. Then we need to worry about galaxies and baryonic effects, and how that is affecting the distribution of matter in the universe. And finally, when we have this, we need to model the uncertainties and how we make this also in a computationally efficient way, so we can sample livelihoods and eventually put constraints on the parameters of our model. Okay, so I'm going. So for the first challenge, I'll be able to create like accurate simulations of the universe. We started by developing a specialized embodied code where we put a lot of effort into having like sub% predictions, numerically converged predictions for the distribution of matter, all the way from like super large scales down to the inner regions of clusters and galaxy size halos. We can these simulations currently are, I would say, the most accurate ones in the universe, in the world, sorry, for the distribution of dark matter in the for a given cosmological model. So we roughly cover regions of about 2 gigaparsecs with 100 billion particles, and that means that we can resolve objects of about 10 to the 10 solar masses. So these were carried out in the Mare Nostrum Supercomputing Center. They took about 10 million CPU hours, and we have 6 of these simulations, right? Each of them on different cosmological parameters. So if you go to this website later, this YouTube video where you can fly through one of these simulations, and if you open it with your mobile phone, you can actually have like a 360 degree view of this simulation. Okay, so this is this somewhat easy part of the problem, right? So numerical dark matter simulations in particular are reliable tools. We're confident that we are predicting accurately what the universe should be like for a given cosmological model. But we need hundreds of thousands of them, right? We need to be able to sample many different values of sigma 8 and omega matter and so on. So carrying out one simulation every time you need to test a given cosmological model would be unfeasible, right? So it would take more computing time that there is available in our lifetimes. So we're using a different approach. So actually, we notice that there are certain degrees of there's regularities and there are symmetries in the simulation that we can exploit to cover this high-dimensional parameter space. So in a nutshell, what we can do is to take one embodied simulation, and we can perform certain rescalings of their unit and mass length, so that they mimic structures in a different cosmological model. So this is, for instance, a comparison in a full embodied simulation that took 200,000 CPU hours, and the predictions of this method that took only 4 seconds. Right? So we have an accuracy of about 20 kiloparsecs on the positions of these structures, and took only a few seconds. So it's 8 orders of magnitude faster. So we have put a lot of effort into validating and quantifying the uncertainty of this approach for many different statistics around here. And this is 2 summary plots of what we are currently achieving. So this is our typical accuracy in predicting the nonlinear power spectrum as a function of scale, right? So the amount of the spatial distribution of the nonlinear dark matter, essentially, and the abundance of galaxy clusters, right, as a function of their mass. So here I'm comparing the predictions of our method against a full embodied simulation with the same cosmology. So each line there's a different cosmology. So we see that there is a scatter of about 1% or so, and overall the range of scales. And for the abundance of halos, it's also about a few percent. So even though it's not perfect, I think this allows us in a super quick manner to start essentially for any cosmological model that we want to try, we can create very quickly the full 3-dimensional nonlinear field of dark matter. And this is going to be the backbone of the modeling that we are attempting. Right, so I was telling you, now we have the dark matter, but in this, on top of this dark matter field, we need to model the effects of galaxy formation and baryons in general. So this is a super interesting topic that connects galaxy formation with cosmology. And I wanted to start by giving you an example. So this is of imagining of two types of galaxies, right? So one sample selected by stellar mass, another by star formation rate. So this stellar mass is what currently surveys have measured, like Bose or Sloan, essentially, right? And so what you have typically is that this stellar mass selection of galaxies will live in halos of about 10 to the 12 and above solar masses, and the galaxies they tend to be with certain velocity dispersion in these clusters, but are roughly at rest within the cluster. But now, if you think of a star formation rate, something that's going to be used for future cosmological surveys, such as Euclid or DESI, these are going to pick galaxies according to their emission lines, right? So it's effectively a star formation rate selection. And now, if you imagine like these galaxies inside cluster will be preferentially picked up in the outskirts. Right? Because soon after they fall into their halos, from pressure and other processes will strip them from their cold gas, and soon after there will be devoid from star formation. So these have a very different picture than the stellar mass selection. Now they tend to have, as I was telling you, to be orbiting or to be in the outskirts of halos, and also with a net infall velocity, right? They're not at rest, but they are kind of all pointing towards the center. So this is it's an effect of purely from galaxy formation, and that has an effect on the spatial clustering. And here's the comparison of a LRG or a stellar mass kind of selection and an emission line selection. Right? So we can see that on a small scales, the clustering is very different, and even on scales of 30 or 40 megaparsecs, they are different. So we need to account for galaxy formation when we make this prediction, when we compare what a given cosmological model should look like and compare that to real observations. So we actually have taken two different paths to tackle this problem. The first one is to try to do a physical modeling, right? So because we have the dark matter distribution and the full merger trees for every structure, we can perform relatively sophisticated modelings of the expected content or galaxy content of a given dark matter halo. So we have chosen to what we call this extended subhalo abundance matching, where the basic assumption is that there is a link between the depth of the potential well inside a given dark matter structure and the amount of stars that it hosts, and that there is a connection between the dark matter accretion rate and the star formation rate that a galaxy experiences. So we have developed this model, and we enhance it with tidal stripping of stars and a tunable degree of environmental correlations. So and then we can go and select galaxies according to different selection criteria, right? So stellar mass or star formation rate. So this is effectively try to model the physics on an object-by-object basis, and then each of these modeling has some certain astrophysical parameters that we can then vary. So and this is an example of what would be like. So for instance, this is the correlation function of galaxies, and this is what happens to it when we vary the merger timescale, right? From the red line, which means essentially there is no, or galaxies merge almost immediately with the central galaxy, or when the merger timescale is very long, means that the galaxy will orbit for many dynamical times before it actually merges. So we see that here there is a large room, right? That all these lines and in between can be thought of as the uncertainty to galaxy formation. We do the same for all the other parameters, and we have validated this approach by comparing it against state-of-the-art hydrodynamic simulations. In this case, Illustris TMG. Okay, but this has a problem, right? That this is even though it's a physically motivated approach, and that arguably is kind of it's some of the most realistic way you can do cosmological analysis. You need to make specific assumptions about the physics and about the completeness of the physics, right? That you need to make sure that there is no yet unknown or simplification in your galaxy model that is not leaking into your cosmological constraints, right? For instance, imagine that you perhaps measured a non-zero neutrino mass, but you need to also make sure that that's actually neutrino mass, and it's not because your quenching model is inaccurate, right? And that is something hard and perhaps even impossible to do. So an alternative path that we are following is an agnostic description of the distribution of galaxies, right? So this is similar to what you would do from a perturbation theory point of view, where you write the overdensities of galaxies, the number of galaxies, as a linear combination of different properties of the field, right? For instance, the density or the tidal field or the Laplacian of the density. So, and you can demonstrate that on large scales, the galaxy overdensity can only depend on those things, right? Because there are only quantities that are allowed by Galilean invariance and these type of things, right? So you can actually do that and write down a model that still brings the dynamics from the numerical simulations, but describe the galaxies in this perturbative model. So with this, this model cannot reach to intra-Halo scales as the other one, but still can reach to scales about 5 times smaller than current models, and with the advantage of being agnostic. So what we are doing is to characterize these proportionality constants I was telling you earlier, right? This B1, B2. This is called the bias parameters. And we can actually measure it in our in our more sophisticated galaxy formation simulations, and measure their values and the degree of uncertainties and what coefficients are allowed by our current understanding of galaxy formation. So you can then use them as a prior for a cosmological analysis. Okay, so that was galaxy formation. Another thing we need to worry about is the effect of baryons in general and of hydrodynamic forces. So if you look at the nonlinear power spectrum, for instance, and you compare it to that you measure in hydrodynamic simulations, you see that on large scales, this ratio is 1, right? It means that dark matter, gravity is the only force you have to worry about. But as you go to smaller scales, you see that depending on what galaxy formation simulation you trust, you end up with a different result. So this is a problem because most of the weak lensing surveys are going to be sensitive, or most of the cosmological constraint comes from these scales, right? From 1 to 10. Right? So if you don't know what the correct astrophysics is, we likely will going to get biased results. So we need to account for this physics. So you could try to assume that one of them is the correct one, but one physics is the correct one, but you don't have you cannot guarantee that the universe is not different than your simulation. So the approach that we're following is, we call it baryonification. And the basic idea is that you take a dark matter halo and you assume that it's described by 4 components. So one is gas in hydrostatic equilibrium, and then you describe it with a certain density profile. Then you have stars and gas in the center, right? That's associated to a galaxy. And then there is a certain fraction of the mass that has been expelled due to AGN feedback, or perhaps even inhibited from being accreted. And then you have the dark matter that back reacts to these changes, right, through adiabatic contraction. So the basic idea is that now we have this physically motivated model that we parameterize in the same way that we parameterize galaxy formation physics. We can parameterize this baryonic impact on or the effect of baryonic physics, and then we take an embodied simulation, and then we can perturb it according to this this model, and then we can vary, for instance, the mass in bound gas, or the mass, or how far this gas is being ejected. So this model, we call this Varification. Then we showed in a series of papers that we can describe all the variety of galaxy formation models. So all the possible impact, right, from the Eagle that predicts almost no baryonic effects to the illustrious simulation that predicts like a 70% or sorry, a 30% decrease in power. So this allows us to take our simulations and create quickly different nonlinear fields that could mimic the effect of any of these simulations. And more importantly, we can vary the efficiency parameters in a way that then we can constrain them directly with data. Okay, so I told you how we can get very accurate simulations for the dark matter distribution, how we can sample high-dimensional parameter space, how we then model baryonic effects and galaxy formation physics inside of this dark matter, right? So now for a given set of astrophysical parameters and cosmological parameters, we end up with a virtual universe essentially in a matter of minutes. Okay, so how do we make this then feasible, right? I mean, you have these huge predictions, and it still might be fast, but it's not, it still is a non-negligible computational challenge to be able to now test, potentially millions of these universes. So the way we tackle this is through the use of machine learning, specifically these feed-forward neural networks, where we pre-compute tens of thousands of different combinations of astrophysics and galaxy formation, and then we train these neural networks on these maps or summary statistics, right? So for instance, we compute the power spectrum, and then we train a neural network with those things, and then we can go and evaluate that neural network in a matter of microseconds. So so then so it becomes very easy to do cosmological analysis and so on. So we have actually so far created these so-called emulators for the linear and the nonlinear matter power spectrum, for the effect of baryonic effects, for galaxy correlations, and for this perturbative bias approach in real and in redshift space. Okay, so finally we can put all these things together. And as a first application, we took the illustrious TNG simulation. This is a full panoramic simulation. We selected galaxies in there. We measured the correlation function. And then in real or in redshift space, where we account for galaxy velocities. So in each of these cases, then that is going to be our data vector. And then our model is our numerical simulations, where we have modeled galaxies and then build an statistics, and then we vary things inside a livelihood sampler. So this is the results. So here you see that the data, the illustrious TNG measurements is this black line. You see on the top and bottom panel, and our best fit model is this red curve. You see that the agreement is really good. They are compatible within the statistical uncertainties. So even on scales that are like less than 100 kiloparsecs, and on scales as large as the finite box of the simulation allows to measure. And here are the constraints on different parameters. For instance, on this is the stripping of stars. And also this is the merger timescales, and they are also varying, for this example, omega mater and sigma 8. So here we can focus on this panel, for instance, and these are the cosmological constraints that we obtain. These are compatible with the with Him1 sigma, with the cosmology adopted by the illustrious TNG, so showing that our approach is unbiased. And these are the essentially posterior distributions on these parameters, and after marginalizing over galaxy formation physics. So these are that I think is quite promising, that we can use even small scales for this cosmological analysis. But one of the, in my opinion, most powerful aspects of this approach is that because we are creating virtual universes, kind of three-dimensional universes, we can project them in different ways. We're not making only predictions for the galaxy correlation function, but we are making consistent predictions for the dark matter, galaxies, and baryons all at the same time, right? So, so for instance, the amount of baryons affects the dark matter, and the dark matter affects the galaxies, and so on. So we can, for instance, if we focus only on dark matter, we can make predictions for lensing. We focus only on galaxies, we can measure, rate space distortions and so on the baryons and Sunyaev-Seldovich or intensity mapping. But then we can make also all sorts of cross correlations, right? Because we have dark matter and galaxies, we know galaxy-galaxy lensing also, and then we can do galaxies SC, or we can simultaneously analyze SC lensing and galaxy clustering, and and eventually clusters and so on. So so I think we are then if you can develop this model, then for instance constraints from Sunyaev-Seldovich can inform about the amount of AGM feedback that there is, and with that amount of AGM feedback we know how much distribution, how much of an effect dark matter suffers, and then know what effect to expect in lensing. Of course, you do this all in a self-consistent way. And also another important aspect is that as our understanding of galaxy formation and cosmology and also the ever-growing computational power keeps increasing, all this will feed back into more detailed and more efficient models, and that will yield stronger cosmological inferences. So I think it's going to be a continuous process where all of our improvement of astrophysics will eventually improve also our understanding about fundamental physics. Okay, so so this is what I wanted to tell you, and so I think as a summary, I think all this new data that is coming in the next decade or so, it's a huge opportunity for understanding about our universe, but it's also going to be a huge challenge. There is still a lot of unused power in this data, and hopefully approaches like the one I described based on simulations, it's going to deliver a more comprehensive and powerful analysis of all these surveys. And this perhaps could lead to a new way of to discover additional physics and understand better nature. So many of the things that I described to you are already publicly available if you're interested. I invite you to visit the website of the ERC project, where we describe various of our projects, or you can download our data, or even like a Python package where you can use our trained neural networks to make your own predictions and even enhancements. Okay, so so that was what my ERC project has been about. So, and I wanted to spend the last few minutes telling you about my experience applying and what I think I've learned in the process of application. So as Patricia said, I got my ERC in 2016 after 2 failed attempts. I think it's but in each attempt, I think I was learning and getting the useful feedback from the evaluators, and I think improving my grant. So these are highly competitive ones. They're about 10%, and it's 1.5 million euros. And the things I learned, I think I would say the most important thing, at least of the process, for me was to force myself to have time to think. So probably, as happens to you, that one is sometimes very busy with projects, and so always have more projects than what you can you can work on, and you're always busy finishing the next paper. But this sometimes what doesn't give oneself enough time to think about what are the big questions in your field, right? And for me, was this question of what is the most important contribution I could do, I could make to science, right? Given my interest, my expertise, what I'm good at, what I'm not good at, and so I think it was a good experience, an opportunity to stop, dedicate a few weeks to say, okay, what is the most important thing I can do, and I think it's and how you actually can achieve that, and make a plan, a realistic plan of what are the steps that need to be taken, and what would be really distinctive things of your science in the next 5-10 years. So I think that is a useful process. I would say, even if you don't end up applying or you don't even get it, I think stopping and think about your sign in a more strategical manner, I think is something that I think was useful for me, and I think would be useful for everybody to really be ambitious and think big, and at least develop what you would like to do with your career in the next 5 years or so. And I think just tips, probably some obvious things. That one is dedicate time to the proposal. I think I think the process is useful, but you also need to dedicate time to it. I think try to put not to neglect the presentation part. I think that is super important, like how to present your ideas clearly and how to make them accessible to other people. And I think I always remember that you have to put yourself in the shoes of evaluators, and not in an evaluator that is nice and relaxed reading your proposal, but in an evaluator that only has a limited amount of time and maybe has many other things to do cannot even dedicate 100% or as much time as you would like to your own proposals, right? So you need to take care of all these kind of the presentation side of your proposal, and don't neglect that. And the other thing that I thought was super useful is to get as much feedback from others as possible. Try to, especially people that don't work on things really similar to you, right? But people that are a bit outside, that can give you feedback on how clear your ideas are and how are perceived by people that don't know about those things. So at the end, my advice would be, I think the process is super useful. I think you have to take it time, not only to write a proposal, but to think about your career and what are the important questions that you can answer and what makes you unique. And if you decide to go for it, I think it's a worthwhile experience, and I think you will learn and I think become a better scientist anyway. Okay, so that was my talk. So thanks a lot for listening and your attention.
Thank you very much, Raúl. Thank you very much for the talk. It's been really impressive, the amount of work that you and your group have done, and thank you also for the advices about how to write an IRC proposal. For the people in the audience, if you have questions for Raúl, you can write them in the chat of the YouTube channel. In the meantime, I would like to ask you, when you evaluate the effects of the barium physics, I guess what you do is that you take the simulation and put it at the end. At the end, you change the parameters, the amount of gas, stars, or how you, I don't know.
Right. So in our model, there are 3 parameters, and then so we are able to predict the nonlinear distribution of dark matter as a function of for instance, the stellar mass of the central galaxy, right? In a kind of halo mass stellar mass relation, right? There is one parameter that controls this.
Okay.
So then we can then that becomes kind of a nuisance parameter, if you want, right? So we have now with lensing data.
But you do it at the end, or you follow the whole evolution? I mean, because for example, to increase, if that galaxy at the end have more stellar mass, the evolution has been different, no? So the forces will have been modified also
Okay, I understand. No, at this point, we don't have a self-consistent time evolution. Right? So we say, okay, at this time, this is what
Okay.
our data prefers. So
Okay.
our idea would be to get, for instance, this stellar to halo mass ratio, this kind of parameter, and then you can measure it at different redshifts, for instance. And then without having to impose a given redshift evolution, you might then analyze that and say, okay, the data prefers something with a given evolution or prefers no evolution, and so on. But we are taking a more like a data-driven approach.
Can you tell us what is your feeling about all these experiments that you mentioned? Like, are they gonna be successful, or do you think we can constrain the bias using tools like the ones that you have presented, or what is your gut feeling?
So I think there are kind of two types of challenges for the future. I think there will be maybe kind of the completely unknown set of physics, and that probably is detecting deviation from lambda from a cosmological constant. Then we don't know whether that is it's at a 1% or is at 10 to minus 10 of a percent. We have no theoretical prior on that. Right? The same for non-Gaussianity. Could be order unity. I mean, there are some arguments to say why it should be order unity, but still could be 10 to minus 2, right? And there are these parameters, right? That we have the opportunity to search for them, so probably we should, but there's really no guaranteed return. And then there are other parameters that I think are should be more safe, right? And one of them is the neutrino mass. So there are already lower bounds from solar oscillation experiments. So we know that cannot be 0, right? It has to be larger than 0.06 electron volts. So on that, and with the accuracy of this next generation service, we should be able to get to that level, right? So if we don't see it, means.
Do you think it's like our last chance already? Like, I mean, at some point we should say, okay, there is no,
yeah,
we haven't found it, no?
Right. So at some point, I guess it would be, I guess, no, we might be going to give up. But I think there are, like, at least for the neutrinos, I think that for the next decade or so, there is like a very clear target that we know that if we get to this, if the experiments perform as they should, we should either say, yes, we detected neutrino masses, and perhaps this tells you the type of extension to the standard model that you need. Or you say, no, we don't detect it, and that, I don't know, there could be because neutrinos are weirder than we think, or there could be, again, we might end up in the same thing as I was saying earlier. We would not know whether it's a theory or a model or new physics. But on the other hand, I think that the really cool thing of this approach is that if you, for instance, have neutrino masses, it's not only that one experiment picks it, right? It's not only lensing that's going to detect. If it should be there, it should be be seen in lensing, it should be seen in galaxy clustering, and there should, it should appear in several different ways. So kind of the complementarities and synergies of different probes is, I think, is something that's going to be quite powerful.
We'll see. Well, I will ask you 1,000 questions, but I see that your daughter is like claiming your attention, so I don't wanna take more of your time. I would like to thank you again. I enjoyed the talk a lot, and I'm sure the rest of the audience, you have audience, and well, I hope see you again soon, and not in an evaluation committee. I hope to see you in something like that.
Yeah, I hope so too. So thanks a lot for hosting and the questions and the invitation.
Thank you, and thank you. Bye to everyone. Thank you very much.